Hello everybody and welcome to week 5 of building scalable distributed systems. This week we're going to focus on some of the fundamentals of distributed databases, including consistency, the architectures they adopt, and we'll cover quickly the CAP theorem and some of the issues to do with ordering of events in distributed systems. Much of that will be left to the reading that's associated with this module. Let me just do an I'm going to cover distributed database architectures, talk about replication using different approaches such as master-slave and peer-to-peer, the issues of consistency and the CAP theorem and ordering of events. So distributed databases are just de facto now at internet scale. These are examples of data centers that internet companies use, and major internet companies have more than 1 million servers, and they distribute their data across these commodity servers in the databases. So this move to distribution has been driven by scale. Simple as that. It's so much easier to distribute data, to make it available because you have multiple copies, and to provide higher performance because you can throw more resources at a distributed system than you can at a centralized system. So distribution is now absolutely fundamental to the data layer in internet scale systems. There's two basic approaches you can use for a distributed database, and these are depicted on the slide here. One's master-slave, where one database holds a master copy of the data and the others basically replicate that master copy, and the other is peer-to-peer or shared nothing, where every node has multiple copies of data, and data will be distributed across different nodes. There's no master, you can update any, and somehow the updates on one ripple through to the other copies that lie around the distributed system. And each has strengths and weaknesses, and we'll talk about those, but of course these are trade-offs. I love this Dilbert cartoon, but I won't pause while you read it, so if you want to read it, just pause the video. It's extremely funny and appropriate, as much of Scott Adams' work is. So, master-slave architectures. With a master-slave, we have one master copy of the data, and writes occur typically to the master. Any system can then read from the slaves. The strength of this is there's a single copy of the master where you can always get a consistent source of truth. That's always the real value is held by the master. Imagine when you're writing to the master, simultaneously you write to the master and then read the same database object, same value from a slave. There's a window of inconsistency there. The time it takes for the update to replicate from the master to the slaves. So there's a chance you may not always get the most up-to-date copy from slaves, but typically this is not a major problem. It's a really nice solution, works very well. Disadvantages, obviously, in terms of the bottleneck of writes at the master. If you exceed the capacity of the master for writes, then you're in trouble. And also, if the master fails, what happens? There's different enhancements to master-slave architecture. So you'd have a multi-master, whereby you partition the data across multiple masters, and each has its own slaves. Or you can just partition the whole database as shown at the bottom, and each has masters and slaves for each partition of the database. But they're essentially the same underlying architecture. So one of the core issues with master slaves is what happens if it fails? The machine crashes, or you just can't see it because maybe the network has crashed that connects you to the master. It may have crashed forever, or it may just crash for a few seconds, a transient failure. So in these cases, you can't do any writes. So if you want to do any writes, you have to elect a new master. So let's assume there's 3 slaves. We elect one of the master, and after the master selection to our slaves, and then we can continue to write to the new master. Maybe at some stage the failed master comes back and there's protocols where we could decide whether that becomes a slave or a new master or whatever. But essentially, if we have 3 slaves, we need to elect one as the master. Sounds pretty. Trouble is, it's not easy in distributed systems. Consensus in distributed systems is actually extremely difficult to achieve. Let's take an example. The classic canonical problem of this is the 2 generals. Imagine we have an army in the middle here, B, and the 2 armies on the other side of the enemy, and they want to attack B. So armies A1 and A2 need to attack B, but to win they need to attack at exactly the same time. If A1 attacks B and A2 doesn't, B will overwhelm A1. And if A2 attacks B and A1 doesn't, B will overwhelm A2. That's not good. So the generals in charge of A1 and A2 need to have consensus on a time to attack. So no, there's no easy way for them to get to each other. They're distributed in terms of space. They have no direct communication channel, no direct reliable communication channel. So how do they do this? Well, the general in Army 1 might say attack at dawn. Send a messenger to Army 2, goes round the enemy camp. But what happens if that messenger arrives and Army 2 sends an acknowledgement, but the acknowledgement in terms of the messenger gets tracked down by the enemy and killed? That acknowledgement never arrives. So the general in Army 1 will not know if his message was received. So let's just assume that the acknowledgement from Army 2 does arrive, and so the general in Army 1 knows for sure that General 2 will attack at the same time. But how does General 2 know that the acknowledgement was received? Well, they don't. And the only way they can know is if they receive an acknowledgement of their acknowledgement. Now, if this occurs, that's good. But if they don't, if that messenger gets attacked and killed, then General 2 doesn't know if General 1 received the acknowledgement, and hence there's no consensus. And this can be proven to be impossible. No matter how many acknowledgements you send, you can never reach consensus between the 2 armies, General 1 and General 2. So essentially in a distributed system you can't achieve consensus. So it's a very hard problem. You might want to think of ways you could approximate consensus. So for example, in this problem, you might want to send 100 messengers every time you send a message. And in theory, the enemy won't be able to kill them all. So a few will get through, maybe a lot will get through. So every time you send 100 messengers, you're using more resources, you're creating more victims, but you have a much higher chance of getting the message through. You never know for certain, but you have a much higher chance. This has implications for a new master election. So the master, the primary, or the leader as it's sometimes called, fails. So first of all, how is this detected? Well, it's detected because the slaves can't see the master. There needs to be some protocol whereby each of the nodes is aware of the status of the others. So let's assume there's 7 slaves. The election must produce a single new master and 6 slaves, presumably, if we have 7 slaves, and take as little time as possible, because if it takes a long time, then our system is not available for writes while the election is taking place. So that's the state that we need to reach at the end. But there's many subtle problems in this. So what happens if the slaves are disconnected from each other? This is a network partition. So we might have 7 slaves, but the failure which caused the master to go down also caused 3 of the slaves not to be able to see 4 of the other slaves. So that's really hard. And then what happens if during the election, the 7 slaves are figuring out who should be the new master? the old master reappears because the network failure that made them seem unavailable was simply transient. It was just someone pulled a plug on a connection for some reason, or a device failed and then rebooted and came back. What happens if the master reappears? These are all tricky problems. Lots of people have studied these, and there are solutions to this. A common one, which I recommend you read about in the reading, is the bully algorithm. It's fairly straightforward. There's many other approaches. A classic one is Paxos from Leslie Lamport, which is incredibly complicated, but it's a very guaranteed way to reach consensus in a distributed system. And if you want to see how the theory of the bully algorithm and Paxos actually translates into practice, there's a nice article there on the approach used by MongoDB to achieve new master election in their master-slave architecture. So that's all part of your reading. Peer-to-peer replication is somewhat simpler because it's masterless. You don't have any master copy that you need to maintain. You can read and write from any copy of the data from any node, and as soon as an update is made to a particular node, somehow the system propagates either synchronously, so it waits for the updates to occur at the other nodes, or asynchronously, the request to update the object is satisfied, and then in the background the node makes sure the other copies get updated asynchronously. So the advantages of this are you can update any node. It's simply you've not got the master problem and the potential unavailability and capacity. Disadvantages, well, you've got a potentially larger window of uncertainty. When you make an update to one node, it may not ripple across to the other replicas, and systems may be reading stale data from other replicas. Also, they may be down, so how do you know when a replica is actually going to receive an update? There's no way to easily bound this window of inconsistency across replicas. Let's just make sure we understand what we mean by consistency here. On the previous module, we talked about ACID transactions, and the consistency there was that in the C meant that when we do an update to the database, we leave its values in a consistent state. And that was an application defined characteristic. It's the semantics of the update are maintained, and they depend on what the actual transaction is doing. In in peer-to-peer networks and master-slave networks, databases, consistency really means replica consistency. So when one copy of an object is updated, how long does it take for all the other copies of that object to become consistent in the face of concurrent read and write operations on different copies and different nodes within the distributed system? So here we're talking very much about replica consistency. And distributed databases will typically use an eventually consistent model. So this is much more optimistic than the pessimistic approach promoted by ACID transactions. By optimistic, we mean that when one update completes on a particular replica, it's assumed that eventually it will complete on the other replicas. So consistency is achieved eventually with some latency. So this is what we mean by the consistency problem in a distributed database. Now, there's something called the CAP theorem from Eric Brewer, and I won't go into the details on this, but it basically says that in a distributed database, if you get a network partition, i.e. the P in the CAP theorem, a network partition means that all of the nodes in the database cannot see each other any longer. There's basically a network failure has divided the distributed system into two halves. If this occurs, you can either maintain consistency or availability, but not both. So whenever you design a system using a distributed database, you have to trade off either consistency or availability in the face of a network partition. And this enables you to think quite clearly about the issues of strong versus replica consistency. Strong replica consistency means that the replicas are always in the same state, they're always consistent, whereas weak replica consistency means that potentially they're in a different state, but eventually, hopefully, they will reach the same state. And also in the reading, there's a technique called quorums, which enables you to provide some measure of strong consistency without having to wait for all the replicas of an object to be updated. Finally, let's just think very briefly about the time and ordering of events in a distributed system. Each node has its own clock in a distributed system, and these clocks are not perfectly synchronized. They drift. And even though you can resynchronize with servers known as NTP servers, it's not always sufficient to solve a problem because not every server has the same understanding of time. The clocks are essentially different. So an event that's timed on one server at a particular time, it may actually, time-wise locally, may seem less than an event that occurred on another server, but in actual wall clock time, real time, it occurred afterwards because the clock was running slow. So what we need to think about in distributed systems is not comparing absolute clock times across nodes because they drift. We need to think about whether events occur logically before other events. So if two updates occur at exactly the same time to a particular data object, which one do we keep? And this is what we mean by determining the order of events in a distributed system. And there's some approaches to doing this, and in the reading you should look at Lamport clocks, the classic approach from Leslie Lamport, which enables you to establish a happen before relationship between events, logical events in a distributed system. And then vector clocks, which are an improvement on Lamport clocks, which enable you to actually determine events which potentially did occur as conflicts, known as siblings, and enables you to programmatically resolve those conflicts. Vector clocks are used in quite a few distributed databases, REAC being an example that we'll look at later. And there are actually more sophisticated but much more expensive examples, as exhibited by Google's Spanner F1 database. They use GPS clocks in their hardware, and GPS clocks are incredibly accurate, so they can pretty much guarantee that the times across servers don't drift. And this makes some things quite a bit simpler. Well worth a read if you're interested. So, in summary, scaling relational databases is difficult and NoSQL technologies are now being used, but they're essentially distributed databases, and distributed databases incorporate and suffer from all of the complexity of any distributed system. The CAP theorem enables us to think about consistency and availability in the face of a network partition. And if we want to logically understand the order of events in a distributed system, we need to use techniques such as vector clocks, which can be used to detect conflicts in weakly consistent data stores, in eventually consistent data stores. That's it for this week. Next week, in detail, we look at NoSQL databases.